So in this lesson, we will be talking about gas molecules, okay? And the chemistry of gas molecules, specifically their pressure. So here we have solid, liquid, gas. As you can see that there are no IMFs between each gas molecule. This is a diatomic gas. So there's no attraction whatsoever between them. But these gas molecules will hit the sides of the container and exert pressure. So today we will be looking at the different units of pressure. So you saw a video of the collapsing Coke can. If you haven't seen it, click on this link. Initially they had a can, it's open, and they have a little bit of water down here in the bottom, liquid water. And they heated the water and turned from liquid to gas. Okay. So some of the gas molecules comes out of the hole of the can as it escapes up. Initially, the pressures are equal. So you have pressure from the atmosphere composed of our atmospheric gases like nitrogen gas and oxygen gas. Okay. Since it's open to the atmosphere right here, there's also pressure from the water vapor. These water molecules are also exerting pressure on the sides of the container. Since the pressures are equal, then the can is neither exploding or imploding. As soon as they put the can in cold water, they put in some ice, what do you think will happen to the water in the gas phase once it gets colder? You're right. They will start to turn into liquid. And so you have an absence of gas inside, which means the pressure inside is lower. Okay, the gas molecules outside are the same. Since there's more pressure outside than inside, the can implodes. And that's what you saw on the video. So gas molecules, because we can't see them, we can measure them in 4 ways. Okay, the first one that we're talking about is pressure. How much force per unit area are they using to hit the sides of the container? Okay, another way we can measure gas molecules are volume. So what we can do is we can trap the gas in a container, and by the size of the container we can see how much gas molecules we have. This could be 2 liters, this can be 1 liter. So the units of volume are in liters, milliliters, etc. Another way to describe a gas molecule is by its mass. Okay, I know it's hard to weigh a gas molecule, but we will use a formula later on to use the pressure, the volume, and something else to be able to get the mass. Okay, and that will also lead us to moles. Okay, another way to measure gas molecules is by its temperature. Okay, in this unit, we will only be using Kelvin. So we will use a thermometer in the lab in the units of degrees Celsius, but we will convert it to Kelvin. And the reason we'll use Kelvin is because there are no negative numbers. Okay, it goes from 0 and up. So now we're going to talk about the units of pressure. So the units of pressure that we'll be talking about are Pascal is the first one. We'll do Pascal, atmospheres, millimeters of mercury, torr, and psi. Okay, so first the Pascal. So what we have here is the unit of Pascal. First, pressure of a gas is created by random motion of the molecules. And their collision with the surface. So you're watching them or measuring how much they collide with the surface. Okay, so what you're doing is you're seeing how much force they're exerting. For example, inside this balloon, that gas molecule or atom, whatever it is hitting the sides of the container with a certain amount of force. And it's also hitting it with a certain amount of area. So pressure is equals force per unit of area, how much area it's hitting on this side of the balloon. Okay, so the unit of force is in Newton. Okay, a Newton is a unit of force that will increase the speed of 1 kilogram mass by 1 meter per second every second. So if you look at this picture right here, take this mass and you're pushing it, you're giving it some force, and you're making it go 1 meter away the first second, and the second second, you're going to make it go 2 meters. So you're accelerating this mass. So you're pushing it or giving it some force. Now, if you're pushing it with a finger, it'll give you more force than if you push it with your whole hand, right? It doesn't hurt as much. If you try pushing that with your finger, it'll hurt your finger. Okay, so if the area that you're pushing it with is very small, let's say your finger, the pressure will be very high. Okay. Now, if you take a big area like your hand, then if the denominator is big, then this pressure will get smaller. So you have to consider the area as well, not just the force. And that is shown here with this gentleman on the bed of nails. So even though there's a big force that he's exerting as he lays down on the nails, the area, if you add up all the areas on the nail, is a lot, which means the pressure, if this number is big, the pressure won't be as high. Okay? So this pressure unit is called a Pascal. And that's down here. PA for Pascal. And it's 1 Pascal is 1 Newton per meter squared. Okay? So examples would be inside a balloon. Another example would be atmospheric gases. Okay, so our atmosphere has nitrogen gas in it, mostly nitrogen gas 78%, oxygen gas, and carbon dioxide, argon, and others, water vapor. Okay, those are also exerting pressure. Okay, this little skater right here is exerting a lot of force in a small little area. So what happens is all that pressure is melting that ice and it's making them slide. Okay, so here are the units. We've talked about Pascal already. You also hear something, a pressure unit called the bar, which you will not be using in this class, but it's good to mention. A bar is 100,000 pascals. Okay. Also, if you are at sea level right here, you are experiencing 1.013 bars at sea level. Okay, so at sea level you have 1.013 bars. It's not very convenient to say 1.013 is just too much. So we're going to call that 1 atmosphere. So from now on, instead of saying 1.013, we'll just say 1 atmosphere. They're equivalent to each other. So at sea level, you're experiencing 1 atm of pressure. Okay, so 1 atm is equal to sea level. And that's what you should remember. Here, this picture shows you, if you're at sea level down here, Earth's gravitational pull will pull those atmospheric gases closer to it. So there's more gas closer, more atmospheric gases closer to the sea level. As you climb up a mountain or go increase in elevation, there's less and less gas molecules. So there's less pressure above it. Okay, so on top of Mount Everest, for example, let's say you're up here, that's about 0.3 of an ATM, a third of an atmosphere. So here you have 1 atmosphere. Up here, you're experiencing only a third of that. Okay, so here you go, Mount Everest, and you're getting about a third of the original. And if you go higher and higher in elevation, farther and farther away from the sea level, and eventually you'll get 0 atmospheric gases. There's the absence of gas molecules, no atmospheric gases. Okay, so the pressure can be measured using something called a barometer. Okay, so a barometer, though, this is how it works. You take an open pan. In that pan, you put some mercury. Okay, mercury is a liquid and it's very dense. So these gas molecules, okay, I showed here that you have some oxygen gas right here, O2, argon, N2H2O, and so on, mostly nitrogen gas. These are all your atmospheric gases. These atmospheric gases, N2, O2, are going to push down on the mercury, and that pressure, let's say it's 1 atmosphere of pressure at sea level. Let's pretend you're surfing. This is you surfing. And you are holding the barometer while you're surfing. Okay, you're at sea level. All these gas molecules are going to push down on the mercury, and it's going to make it climb up this column it's a tube. Okay, this is just an empty glass tube that they've taken all the air out. It's now called a vacuum. There's a vacuum in here. Okay, so now it's going to rise, and all you have to do is take a ruler, measure the height of this mercury, and if you use centimeters, it'll be 76 centimeters. If you use millimeters, it'll be 760 millimeters. Since you use mercury, it's 760 millimeters of mercury. Okay, so that is how high the mercury will go up at sea level. So you have to remember that at sea level, which is 1 ATM, the mercury will go up 760 millimeters high. Millimeters of mercury. Okay, you can also use water in this column, but since water is not as dense, this tube needs to be really, really long, and it's going to go up very high. So they use mercury. It's a convenient substance. Okay, so now this barometer was discovered by a gentleman named Evangelista Torricelli. Okay, so since he invented the barometer, there's also a unit called the torr, and it's equivalent to millimeters of mercury. So 760 millimeters of mercury is the same as 760 torr. You can use either or. So what that means is 1 ATM is equal to 760 torr. Okay. Another unit of pressure that you might be more familiar with is the PSI. It stands for pounds per square inch. Okay, and that is the force per unit area. Okay, your tire pressure is about 40 PSIs, and you can measure it with a tire gauge. Okay, so let's summarize what you just did down here. We learned that 1 atmosphere is the pressure at sea level. It is equivalent to 760 millimeters of mercury. Since Torricelli invented that, it's also equivalent to 760 torr. In Pascal, it is 101,300. If you don't want to use all those zeros, change it to kilopascals. Okay, to do that, you're going to go like this. 101,300 pascals. 1,000 Pascal is equal to 1 kilopascal. So 101.3 kPa. Same thing. And lastly, in your tire, it is 1 ATM is about 14.69 psi. Okay, so you have to remember that. There's one last thing that you should know, and that is standard temperature and pressure, called STP. Okay, STP is needed to compare data using the same conditions. Okay, for example, if you have a balloon and you put it in cold water, that balloon will shrink because the temperature is different. If you are at sea level, the balloon will be a certain size, right? As you climb up to space, there's less air on the outside and the balloon, and there's more pressure inside, and the balloon expands. As you can see, this balloon is bigger than when it was lower, closer to the earth. So therefore, you have to make sure the pressures are normalized, okay? So to compare data, we'll tell each other, let's keep the standard temperature at 0 degrees Celsius, and let's keep standard pressure at 1 atm. So if I were doing an experiment and I say, oh, I have a balloon and it's 1 liter in my lab, okay, in San Diego, nice and hot in San Diego. If I call somebody in Alaska, that same, let's say this is 1 mole of a gas, okay, that same gas in Alaska is going to shrink, right? So now it's only 0.5 liters. And I call my friend and I say, what is your volume? And they say it's 0.5 liters. And I said, well, I got 1 liter, so you're wrong. No, the reason they're not wrong is because they're different conditions. So I have to say, can you normalize it? Can you make sure you measure it at the same conditions? Once we have the same conditions, then we can compare our data. Okay, so standard temperature and pressure is 0 degrees Celsius, 1 atm. If you change this to Kelvin, you add 273. 0 plus 273 is 273 K. So memorize those.